Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with your homework. Specifically, we're going to look at Chapter 2, numbers 59, 61, and 65. So each of these problems has a graph drawn with it. So for number 59, you need to just focus on just this graph. The other two graphs are for the other two problems. And it's very important when you're doing any of these problems, make sure you're very clear about what type of graph you're looking at. This is a position graph. So in class, that's where I would typically put like x against t. And I even try to make the colors match here. Whatever particle this is describing, the position function here looks something like this. And now I want to take a look at this where it says, by taking the slope of the curve, verify that the velocity of the jet is 115 meters per second at 20 seconds. So 20 seconds on the graph is about here. Now remember that velocity is delta x over delta t. And you have what's called average velocity and instantaneous velocity. This equation gives what's called the average velocity. The question is asking for the instantaneous velocity. And the reason I know that is because it says at 20 seconds, at a very specific time. It doesn't give a time interval. Now remember that velocity is the slope of a position graph. So if I were to pick two points on this graph, like maybe here and here, the slope of the line between them would give an average velocity in this region. Now, they're asking for the velocity at that point, and the instantaneous velocity is described by the slope of a line that comes in here and just touches just once. That's called a tangent line. There's a couple ways to work this. Method number one, you could draw the tangent line, pick 2 points on that tangent line, and find the slope. Because of the nature of the picture and how this problem is how the picture works, I don't think that method will work very great. I think what you should do instead is this. Pick a point just before and a point just after. And notice if I draw a line through these 2 points, it's pretty well the same slope as the slope of the tangent line. So that's how I suggest you work this problem. Pick a point just before the 20, just after the 20, find the slope of the line between those 2 points. And these are numbers you can read right off the graph. There's plenty of data here. They give you a time, and then you can read this over here to get the position. Same thing here. Time, and then read it off here to get the position. So that should be enough to get that one rolling. Part B, where it says by taking the slope of the curve of figure 2.61. Okay, I didn't draw 2.61 in my picture, but 2.61, it's on the upper right hand page, and it gives you a velocity graph. And just pick any 2 points. If you look at the problem, you'll notice it's linear. You got to see the picture to see what I'm talking about on the upper right hand part of page 85. But the acceleration is slope of a velocity graph. So and by the way, that graph is linear. When you're actually looking at page 85, you'll see what I mean. Pick any 2 points on that line, find the acceleration, or find the slope, and you'll have the acceleration, and you'll be done. So that's probably enough on 59. Let's talk about 61. So 61 is a similar type of problem. It says, using approximate values, calculate the slope of the curve to verify that the velocity at 30 seconds is 0.238 meters per second. Assume all values are known to 3 significant figures. So the picture for it is right above it. And, whoops, it's another position graph. I thought it was a velocity graph. My bad. And that graph looks something like this. And again, this is figure 2.62 in your textbook there. And it says, calculate the slope of the curve to verify the velocity is a certain number. Now you'll notice that this thing is basically linear. And because it's linear, I mean it's pretty close to perfectly linear, that means you can choose any 2 points on this line to calculate the slope. So pick 2 points that you're reasonably confident in the value. So you might choose like this one and this one. You're going to get the times here and here, there's your delta t. And then you're going to get the positions by reading it right here off the graph and right here off the graph. And that difference right there is going to be your delta x. And then take your delta x, divide by your delta t to find the slope. That's pretty well it. All right, let's talk about number 65. Okay, so it says, a graph of velocity against time is shown for a world-class track sprinter. See figure 2.67. So I'm looking at figure 2.67. It's on the upper right-hand side of the page. The first thing I notice is it's a velocity graph. Roughly speaking, it looks like this. It's linear in the first part of the graph and then horizontal second part of the graph. So you should be looking on at your textbook here. You should see a picture roughly like this, and it's got numbers along here and along here. And it says, what is the average velocity in the first 4 seconds? Now you'll notice that the first 4 seconds were here on the graph. And the numerical value up here, to me, it looks like about 12 meters per second. Now, what this graph means is that at t equals 0, the velocity is 0 meters per second. And at t equals 4 seconds, the velocity is 12 meters per second. Now, the average velocity is equal to delta x over delta t. You notice I put a bar over it, and I don't always put the bar. In general here, not just in physics, but in a lot of different areas, that bar there is the mathematical way of saying average. There's a couple ways to get the average velocity. I'm going to suggest this. Just directly calculate it, delta x over delta t. You can't get the delta x is not directly given, but you can calculate it in this problem from this area right here. Remember from class that the area under a velocity graph gives the delta x, or the change in position. So you're going to get that from that area. It's a triangular area. The delta t is 4 seconds, and that should get you through the problem. Part B, where it says, what is the instantaneous velocity at 5 seconds? Well, 5 seconds is here on the graph. Just read the velocity right off the graph. There's not too much about that. Part C, what is the average acceleration between 0 and 4 seconds? So for part C, it says acceleration, average acceleration. What is it? Well, remember how acceleration is calculated. Delta V over delta T, and it's important to recognize that's slope. Slope of a velocity graph. So you're looking for the slope of the line in this region. And then, let's see, what is the average acceleration? Oh, part D, what is the time? What is his time for the race? Part D, time for the race. Okay, as I read the problem, it says it's a 100-meter race. And that 100-meter race, that's the delta x. And the graph looks like it goes to 10 seconds to me. So, I mean, one possible answer, you'll have to look this up, is it might just be the 10 seconds. I'm not sure. If you look that up and it's not right, do this. Imagine this goes out to some unknown time. And let's call that distance delta t. The 100 meters would have to equal the total area under the curve, including the triangle and the rectangle. So the 100 meters is going to equal a number, which you can get from the triangle, the area of this triangle, plus the area of the rectangle. From here to here is 12 meters per second. And then from here to here, let's say, is an unknown time. You should be able to solve that for the delta t. Get a number. And then add it to the 4 seconds. That'll give you the time. So that should be enough to get that problem done. Hope this video helps. Have a great day.